Good morning, folks. Dr. Charlie Hall here, holder of the Ellison Chair in International Floriculture at Texas A&M, and it's my privilege to welcome you this morning to our webinar, Managing Water Quality in the Green Industry. And we've got a great speaker this morning, but before we get to that, let me mention our sponsors. We have a grant from the Southern Region Risk Management Education Center, which helps offset the cost of providing these webinars for you, and that's why we can provide them free of charge and not charge you anything. But also, we have sponsorship from the Texas Nursery and Landscape Association. So many thanks to both of these sponsors that have been bringing the webinar series to you now for almost 4 years. So we've had a lineup of great speakers, and we have all those webinars archived. And we've got one more great one that we're going to archive in just shortly under an hour. So we get started today. Of course, a few instructions about how to maneuver the webinar. If this is your first time, it may seem new to you, but many of you are old pros. As I look down the attendees list, several of you have attended our webinars before, so thanks again for being here. But your screen will look something like this. So you'll have a control panel there, usually on the right side of your screen. And if you look on that control panel, you can open and close your panel by clicking on that orange arrow that points to the left. So that'll open and close and toggle that if you don't want it to be on the front of your screen all the time. And then also you can adjust the size of the window in which you're viewing. If you have difficulty seeing it, you can actually set it full screen by clicking on View and clicking Full Screen. Now, if you have any audio difficulties, if something goes wrong with computer speakers or what have you, you can actually dial in using your telephone and just click that information, and it'll pop up with the dial-in information and the audio pin that you'll select. Now, all the questions are going to be addressed at the end today. I've got everyone muted just so that we don't have a lot of feedback issues, and we can maintain top quality audio today. So you can't ask your questions by voice, but you can type those questions in the questions box that's in the control panel. And if it's a question that deals with the information that Rosa is talking about at the moment, I may interrupt her and ask her that question. But for sure, we'll get to the questions at the end. Now, speaking of the end, when we're finished up, you're going to be directed to a very short, I think, 5-question survey. And that survey is very important in terms of helping us identify not only the topics that we want to bring to you in the future, but it gives us a great idea of how well we're doing in bringing this information to you. And it gives justification for our sponsors to continue sponsoring the webinar series. So please fill that out. And today's session is being recorded, and you'll be getting an email probably sometime around the same time tomorrow with a link to the recorded version. So if you get called away for some reason, no worries, you'll be able to access it. Now, I mentioned our speaker. I'm very excited to have Dr. Rosa Rodales with us today. Rosa is a brand new PhD out of the University of Florida, and she has worked in the water quality area all through her PhD program under the tutelage of Dr. Paul Fisher, who is known, of course, for knowing a little bit about water quality himself. So I had the privilege of serving on Rosa's committee as an adjunct member here from Texas A&M, and so it's been a privilege working with Rosa, and her depth of knowledge is very impressive. And this particular issue is one that obviously the industry is wrestling with. We have a number of water problems, from water quantity and access to water to water conservation, and of course addressing water quality, and that's going to be the subject of Rosa's presentation today. So Rosa, I'm going to go up here to the control panel, and I'm actually going to give you the presenter privileges, and you'll be able to take us off from there with your own slide presentation.
Okay. Can you see my slides and can you hear me?
Well, we can hear you.
Okay.
I'm not seeing your slides yet, though.
How about now?
No, I'm still just seeing the managing water quality in the green industry. There we go. Perfect. Yeah, we can see and hear you perfectly now. So take us.
Okay. Sounds good. Thank you, Charlie. So again, like Charlie, before starting, I would like to acknowledge our sponsors. And I've been sponsored through my program by the University of Florida IFAS Extension, by the Floriculture Research Alliance, and by the Water Education Alliance for Horticulture. So I invite you to visit their websites, and you'll find a lot of very good information in there about water and other topics. So when we talk about water quality, the first thing we need to start thinking is how water sources differ in quality. We have water treated that comes from the municipality or well water, which is considered high quality. And this is water that in general is very clean. We have to think about the chemistry of the water, but in general, besides the chemistry, you can almost directly use this water in your irrigation. In contrast, we have catchment ponds and tanks or reclaimed water, which is considered lower quality water. And you can see on that picture that comes from a grower here in Florida. He's capturing rainwater and runoff into that pond. You can see that it seems to be a system that's very dynamic, very rich in algae, very turbid, a lot of plants, and even big animals around it. So you can imagine how problems can arise by using this water directly as it is. So I'm sure you all knew this, but something I want to ask to you, and if you know this, on the question box, go ahead and answer this question. What is the cost of irrigation water in your operation? It's very important that when we're trying to make decisions about how we're managing water, we understand what is the cost of irrigation water and then contrast that to the other alternatives of managing water. So I'm going to show you some scenarios of the cost of water of some of the growers that we work with. To start with, we have a grower that uses well water. He uses 21 million gallons of water a year. And then the cost of building the well, depreciation of 40 years, also the cost of purchasing a pump depreciated over 20 years, and then the cost of pumping water and the electricity that implies annually cost to this grower 17 cents per 1,000 gallons of water. Then if we look at the fertilizer, we see that of the growers that we've surveyed, the range was between 85 cents to $2.50. Just to make a fair comparison, I put $1, and then we end up with a price of $1.17. So we can see that in terms of this type of water, fertilizer is the most expensive part of the nutrient solution. If we compare this with pond water, the second grower uses 10 million gallons of water per year. The price is a little bit higher, and that's because this price includes the price of building the pond, of pumping the water, but also the price of filtration and chlorination, because pond water in any surface source needs to be filtered and treated before use. And then we add the fertilizer, and we have a cost of $1.35. And then we have a third scenario. This grower, both rows belong to the same grower, but this grower has two different sources. The first source, he uses 8.6 million gallons of water per year. He pays $3.75 to the municipality, and this is the price of a grower in Michigan. He adds $1 of fertilizer to those 1,000 gallons, and then the price of water is $4.75. This grower has capture tanks and filtration systems to recirculate the water, and recirculates a total of 32.8 million gallons per year. The cost of just recirculating this water is 24 cents. He doesn't add more fertilizer because it's already fertilized, and then the cost of the nutrient solution is very low. So we can see that there are economic benefits on recirculating water, either in terms of savings of the cost of fertilizer, but also when we have water sources where the price is very high, we're also saving in terms of the cost of water. So this is all very good that we have some savings, but we have to see what are the issues with recirculating water. So The irrigation water quality parameters that we're interested in are, first of all, the biological, and we'll talk a little bit more in detail about those. We have the physical parameters and the chemical parameters. Today, I will focus mostly on biological and physical water parameters. When we think about the biological water quality, the factors that we're interested are pathogens, biofilm, and algae. We know that pathogens, their presence can lead to plant disease. We're still learning more about how much pathogens in the water can actually lead to disease, but in the meantime, we can just know that the presence of pathogens can lead to disease, and just as a risk management strategy, if we find them, make sure that we consider them to be a risk. We know that pathogens reported in the irrigation water include Phytophthora species, Pythium, true fungi, bacteria, viruses, and nematodes. So we have that whole gamma in pathogens that can be moved through water. Followed to that, we have biofilm. And I would say biofilm is probably the most common problem that we're looking in the greenhouse industry. And we know that if we have over 10,000 colony forming units per milliliter, that can result in clogging of emitters. And the colony forming units is something that a standard measurement on lab that indicates specifically how many units form an individual colony. And bacteria is generally what's used as an indicator for microbial load. So this is a picture that, even though it seems real, are real pictures from two of our growers, one in Florida, the other in Pennsylvania. And what you can see, it's a very costly problem. The grower here on the right, he estimated to spend $153,000 per year just on cleaning and using solutions to clean those pipes and clean the emitters. So it's a costly problem that has to be dealt with, and that's very commonly found in the greenhouse industry. And last, we have algae. There is no clear threshold of how much algae can be a problem, but we all know that algae can clog emitters. It can reduce plant growth because some algae species release toxic substances. It can also provide food for shoreflies, and shoreflies can move pathogens from one plant to another. And it can also form an impermeable layer on the surface, like the one in the picture, which you can imagine results in uneven irrigation. So the treatment for this is to use filtration and sanitizer. And I hope that by the end of the presentation, you have a very clear understanding why sanitizing of the water has to go hand in hand with filtration. You can't do sanitizing of water without filtration. And then the physical water quality, the factor that we're looking at are total suspended solids. Here the thresholds are defined a little bit better. We know that if we have over 100 parts per million of total suspended solids, that can result in higher risk of clogging of emitters. We know that established by EPA that over 20 parts per million can affect the efficacy of sanitizing agents, and that's the recommended dose for non-edible crops. The recommended dose for edible crops is, I think, 5 parts per million. So the treatment for this is filtration, and we're going to talk about filtration too. So today I'll talk about monitoring, and we're going to monitor the problems that I just mentioned before. We're going to talk about filtration and sanitation. So first, monitoring. Monitoring pathogens is very important, and unfortunately to date, we can't monitor pathogens on site. We need to get the samples and send it to our lab. There are a few groups who are doing research on how to monitor pathogens on site, but we still don't have those tools available for growers. So the alternative when a grower sends a sample to a lab is that the samples will be either plated or they will be scanned by doing DNA fingerprinting. If the samples are plated, like the one in the picture here, the results that you will get are either at the genus level, Pythium or Phytophthora. It may or may not be pathogenic, but if you get a result saying that you have the presence of Pythium or Phytophthora, assume it's pathogenic and reduce your risk by doing it, by following up with a treatment. An example of a lab is the University of Massachusetts. They charge $50 per sample. Return time is 2 weeks. And then the other alternative for DNA fingerprinting, it's a little bit more specific. It gives you up to the species level. And an example of a lab that does that is the University of Guelph for $195 per sample. And the return time is 1 week. So these are just examples of labs that we have worked with in the past, but I'm sure that if you ask around on your cooperative extension services, there's a lab locally that can do the services as well. So try to use those before
Hey, Rosa,
any other lab.
let me interject here and say that we had a few video issues in terms of part of the screen being cut off or part of your slide is being cut off. I'm not sure if there's a way that you can modify that. Are you showing your slides full screen?
Yes.
Okay.
So what's the part that's cut off?
Well, it like we couldn't see 1 week. Yeah, we're still having that issue there. So I'm not sure what the issue is.
Let me show the whole screen because I was just showing PowerPoint. So let's see that. Does that make a difference?
Yes, it did. We see more of it now, and I'll just instruct folks that if you can adjust the size of your window. When I went to full screen, I actually saw more. And you can actually zoom it to 50% and so forth. But
okay. So now shifting onto monitoring biofilm. You can monitor biofilm directly, very simply by cutting a pipe. We love to cut pipes because that's where we see how things are going on. We can see that when you run clear water, what you will get most likely is just biofilm. And when you put fertilizer in the solution, you will get an algae biofilm complex. We also suggest a lot that an easy way to monitor biofilm is that you include a segment of clear pipe on your irrigation. And make sure that, but you have to make sure that that section of clear pipe is covered to prevent light to go through it, and you just uncover it when you are monitoring whether there's biofilm or not. So that's an easy, straight way to monitor biofilm. Or you can also monitor.
Rosa, let me interject one more time. We're still having some of those issues, I'm told, by some of the folks. So maybe it may not even be the PowerPoint. Actually, within that PowerPoint window, if you could make it just a little bit smaller there, so we can see we can see the whole slide. So maybe instead of going to the PowerPoint itself, you just go through the slides in this view.
Okay, sounds good.
Perfect, because we can see the whole slide now.
Okay, good.
Okay, great.
Okay, so now, no problem. So we can also monitor biological load by measuring colony forming units. And like I said earlier, what you want to count is how much bacteria is present. And you simply send this water sample to a lab, and it's a very standard procedure in labs. Alternatively, you can also use the Petrifilm method. And this method is something that a lot of our growers have tested, and they really like it because it's very simple to use, and they can just dilute their water sample, put it on that Petrifilm, which is just dehydrated media, same concept as a agar plate that I showed you in the previous slide, and then you put it on your slide and forget about it for a while, and 2 days after, you would count how many colonies you have. And we know that if you have more than 10,000 colony forming units, you have high risk of biofilm. So this is a very quick way to monitor biofilm. And this is an example of research that was done by Dustin Meter in our lab. And what he did is he tested the Petrifilms on different waters on a survey that he carried out throughout the U.S. And what's very interesting to see here, you see this different sample types. You see how much bacteria was estimated, and the different methods indicate difference statistically from one sample to the other. So the interesting thing here is that water sources are in general very clean. Just moving the water from the water source to the farthest outlet, meaning that first emitter that's going to touch the plant, you can see how there's an increase in aerobic bacteria when this water goes back to the tank or is moved through the ebb and flow system. You can see how the number of bacteria increases dramatically. And when that goes back to catchment ponds, the numbers are even higher. So this just reinforces the importance of why we cannot use pond water or even catch water on tanks back directly to the irrigation. It needs to be treated prior to that. And then you can also do algae lab tests. Some people suggest that it's very important to identify the specific bacteria that you have present in your lab, in your water, and that's because you can match better the algae site if you know specifically which bacteria you have. It's a little pricey. It costs $150 per sample, but it's something you can do once in a year or twice in a year to make sure that the algae site you're using is more effective. And I suggest that you follow into that fact sheet that was done by Diane Camberato and Roberto Lopez in Purdue, and that will help match the specific algae site to specific algae if you identify which algae you have in your water. And then another easy way to do it on site is to use a kit that is sold by Lamotte. And it's very easy, but it's just qualitative. It tells you if it's really green, you have a lot. If it's lighter, you don't have that much. The numbers can be estimated specifically with the kit, but you need more lab equipment. But if you just want to sample your pond water and see how dirty it is, that's a quick way to do it. And now monitoring physical water quality parameters is something that needs to be done in the lab. In most labs, any soil labs can do the total suspended solids estimation. And again, remember those two numbers. Under 100 parts per million is the target to prevent risk of clogging, and under 20 parts per million is the goal to reuse water on non-edible crops and have effective sanitation. And then particle size distribution, it's really just useful to indicate what's the pore size that you should require to remove suspended solids. And I'm going to show you some examples on how we have used particle size distribution to make decisions. So moving on to filtration. When we're thinking about recirculating water, the filtration alternatives that we have are cascade filters, different types of screen filters here. You see a vibrating screen. We also have those that are commonly called paper filters. We have drum filters, which come from the fish industry. They seem to be very promising for the greenhouse industry. We have sub-filters, and we also have media filters that can have either crushed glass or sand media, and they can all be used for recirculating water. It's very important, again, and I'm going to emphasize this many times because it's something that has to be on the core of water management, that we have to filter first to reduce the demand of sanitizers. And that's going to help to reduce the chemical costs and also to increase sanitizing efficacy. So sanitizing demand can be explained with this picture. What you see is that, for example, if we inject a total concentration of 5 parts per million, and then we measure how much is left, that's called the residual. So we have a residual of 2 parts per million. So that means that there's a demand of 3 parts per million. If we filter, we're trying to reduce that demand and therefore applied less initially and also have more residual if possible. We also, what we did here when we were evaluating the filters is that we wanted to know if the different filters that are used in the greenhouse industry are actually removing suspended solids. And this is an example where we evaluated paper filters and we measured how much suspended solids we had before and then how much suspended solids we had after. And you can see that there was a 50% reduction. We evaluated the other filters here, and what we see here is you have the different types of filters. The first group are all paper filters up here, and these are all screen filters here. And then we measure the concentration of total suspended solids. So what we learned is that total suspended solids in most of the systems that we evaluated, and these are all recirculated systems, you can see that the red bar is the before, the white bar is the after. You can see that even before filtration, the target under 20 milligrams per liter was achieved. So that's one thing that's very important. We know that even though we're thinking about having a high total suspended solids load, it's not as bad as we thought it would be, on one hand. The other thing that's very important to see here is that if you see this very high bar here, you see that the dirtier the water, because this one had the higher load, the more that it's removed. So when we're thinking about deciding on filtration, we have to think that if we understand the concept that the dirtier the water, the more that's being removed, we can understand why it's very important to have different stages of filtration and have a good first stage filtration to remove the big chunks that will remove the most. And then the third thing that we learned from here is that in general, most of the filtration, both the paper and the screen filters, in average, remove about 50%. So again, as we're thinking about staging and designing systems, we have to consider that each stage removes about 50%. But another thing that we need to think about when we're selecting filters is that we need to think about what the pore size we have to match. And I would like growers to start switching from using the mesh system to the micron system. Here as a reference, you can see that we have a 60 mesh is equal to 250 microns, 100 mesh equal to 149 microns, and so on. So keep the micron size in mind, just because we're trying to match the particle size to the pore of the filter. So we analyze particle size by sending our samples to the physics department here at the University of Florida. And what they did is that they estimated the size of particles and how many of those particles were present. And this, what we learned here, I said it's very important, very interesting, and essential to keep in mind when we're thinking about filtration. What you're seeing in this graph, we have the different operations on the x-axis, and then we have the median particle size, the diameter of the median particle size. And as you see, the median of most operations is 140 microns. What this means is most 50% of the particles are greater than 140 microns. 50% of the sample of the particle size are under 140 microns. Again, as we're trying to decide on filter size, it's very important that we keep this in mind. And as you can see, it varies a lot by the operation, so it's very important that you estimate what the particle size is in your specific operation. Going back to this mesh and micron size, we saw that the median suspended solids that we saw in irrigation were 140 microns. So as we select filters, try to think that you don't need to go that low in the micron size of your filters. We've heard a lot of people buying 5 micron filters for several reasons. One of them is that they are promised to remove pathogens, and that's one thing I would also like you to take from this talk today, is that these types of filters that I've mentioned today, none of them will remove pathogens. If you're trying to remove pathogens, the only alternative is to use membrane filtration, because Phytophthora zoospores are 7 to 10 microns. So they're pretty small, they won't go through those filters, and I would like that to be something that you keep in mind, because I've heard a lot of people buying 5 micron filters to remove Phytophthora zoospores, and that's not the case. So now, how does all these total suspended solids and these particles I've been talking about affect the sanitizing agent demand? So this is a research that also was carried in our lab by Dr. Huang. And what you can see is that he applied chlorine concentration. He applied at 2 parts per million. And then he put to that concentration an increased concentration of peat. And that's what you see here in the x-axis. And what you see is that when he measured chlorine level that was residual, after 2 minutes, the concentration goes down, indicating that those 50 milligrams per liter of peat up here exert a demand of 0.5 parts per million of chlorine. So we know that if we have dirty water, the demand increases, or in other words, the concentration of available chlorine decreases. He also evaluated this on other sanitizers, and what you see in this graph is he tested different sanitizers, you can see them here, and he measured how much of the active ingredient was lost. So the higher the bar means that more of the active ingredient was lost. And the different letters on the bars indicate difference statistically. What we learned from this research is that Copper is both here, first copper nitrate, then copper ionization. Both of them, we only lost under 10%. Very little was lost, so they're relatively insensitive to the presence of peat in the solution. On contrast, we have chlorine dioxide, which is this bar here. We can see that chlorine dioxide is very sensitive to the presence of peat. So more than 50% was lost after an hour with the presence of 50 milligrams per peat. And then a similar pattern we saw with hypochlorous acid or liquid bleach. A lot was lost. And then the final products here are hypochlorous acid with peracetic acid. These are products like Sanidate, Xeritol, and you can see that they are relatively insensitive to peat, meaning that when you put peat, the concentration of that active ingredient maintains relatively the same. We also wanted to know how efficacy was affected, because one thing is the active ingredient, but what really happens to the pathogen is what really matters at the end, right? So what we did here is that we had a solution where we put peat, we then put the pathogen, so we're simulating to have this dirty water, and then we put chlorine at 0, 2, and 4 milligrams per liter. And then we measure with deep tomato leaves after 10 minutes and see what was the effect on infection. So what we learned here is that if there's no chlorine, and this is this blue bar here, we have a high incidence of infection. As long as there's chlorine, even when we have peat, the incidence of infection reduced dramatically. So chlorine was still effective in controlling Phytophthora, even in the presence of suspended solids in laboratory conditions. And this is another way to see that same data. We see that if there's no pathogen, there's no disease. If there's pathogen and no chlorine, we see infection. As long as there's chlorine, it did not matter how much peat we had, the disease incidence was very little. So this might sound to you like I'm contradicting myself by saying you have to filter, but we still see control. And what I want you to take from here is what we learned here is we still need to filter because it's a risk management strategy that we're taking. So we want to reduce the risk. The more that we control, the less the risk. So we're controlling risk on one hand. But on the other hand, what we're learning is we have to clean our water as much as possible. We need to filter it. But if you have, but the water doesn't have to be entirely clean because chlorine, in this case, is still doing something. So you still need to filter, but you don't need to filter like it's drinking water because it's not that much needed. And now another important criteria for decision making is the cost of filtration. And I'm just going to give you an example here of the cost of a case and vibrating screen. And this is under an operation that uses 15.2 million gallons per year in phosphorus and recycles 83% of the water. What you can see here, and I want you to just focus on the per 1,000 gallons, is that the consumables are under 5 cents, the labor is relatively cheap, and bottom line, the cost is 16 cents per 1,000 gallons by filtering with a case and vibrating screen. If we contrast that to a clear stream paper, and these numbers come from that same operation as I showed you in the previous slide, what you can see is that consumables alone here are almost the same price as the total cost of the case and filter. Again, going back to how we're thinking about treatment and system design, we have to understand that if we have a filter that has high consumable cost, that should be put at the end of the filtration system. And you have to put at first stages of filtration, those filtration systems that are least expensive or cheaper. So key points on filtration are, first of all, the target is to have under 20 milligrams per liter of suspended solids to reduce the demand. We want to have as much residual sanitizer as possible. We need to filter to smaller particles than the pores of the emitters. We highly suggest that you have at least 2-stage filtrations for recirculated water. Start with a screen filter, typically at the first stage. It's cheaper and it will remove most of the big chunks. And then go to finer pores that are a little bit more expensive as the last stage, but that will also reduce your cost. And then going back to the pathogen issues, media filters can remove pathogens, but because it removes the pathogens that are embedded on organic matter. So it basically removes organic matter, and that's how pathogens are being removed. But you also need, and that also reduces sanitizing agent demand. But free-living organisms like Phytophthora, cellospores, can only be removed by membrane filters. Now we're going to move on to sanitation. And I have some animations here, but it's okay. Basically, what I want you to know from here is that we have different types of sanitizers. In the greenhouse industry, we're using chlorine, chlorine dioxide, copper ionization, copper sulfate, hydrogen peroxide, ozone, more ecological alternatives such as slow sand filtration, constructed wetlands, and UV. I'm going to try this slide, just this slide, because otherwise you won't be able to see it. But the first thing you need to know is whether the alternative that you're keeping in mind is effective to control your problem. So that's why we talk first about monitoring. You need to know what your problem is, right? And then you need to know what alternatives match the problem that can be controlled. So we did this tool in the watereducationalliance.org. If you go to the website, you click on Grower Tool, and then you click on Waterborne Solutions. What you will get is a database where we have summarized all the information where there's published efficacy data for the different organisms and treatment systems. So you can do your search by organism or treatment system. So for example, you're interested in using ozone. You go here, you do your search by treatment system, and you will find the pathogens where it's known that ozone can control. You're using copper. You want to know whether copper is effective. So you can use this tool to understand whether the system you're using has been known to be effective. So it's a very good tool to make decisions. So I'm not going to go through all of those, but I'll just give you an example of chlorine. So what you're seeing in this graph, you're seeing an increased concentration of chlorine here, and then you see the different pathogens where there's published efficacy data. What you see is that different concentrations, it becomes very complicated when we're trying to make a decision of how much to dose. Because you can see a lot of the pathogens are controlled here, but we have a lot of resistant pathogens who need more than 4 milligrams per liter of chlorine. We also know that depending on the crop, more than 2.5 parts per million of chlorine can be toxic. So it's important to know that if we have such problems like fusarium or viruses or nematodes, chlorine might not be the best idea because we know that they're pretty resistant to chlorination and will risk phytotoxicity. So this is the way that I would like you to go and use the tool to understand what are the alternatives and what's really known. And now I will cover a little bit on examples on how the chemistry interacts with chlorine and how other factors should be considered, because the efficacy data that's summarized here, most of them it's done in the lab conditions where other factors have been excluded. But reality is that in the greenhouse industry and on your operations, a lot of other things are going on. So for example, we have that water chemistry can interact with sanitizers, and high pH makes chlorination less effective. So this is something that we need to understand. So here we have the increased pH, and then how much of the total chlorine is in the form of hypochlorous acid or hypochlorite ion. We know that hypochlorous acid is the stronger form of sanitizer, and that hypochlorite ion is the weaker form of sanitizer. They're both part of the total chlorine. They're just different forms. We know that at pH of 7.5 or less, hypochlorous acid is more abundant. So the strongest form is more abundant under 7.5. So if you're using chlorine, you want to adjust your pH to under 7.5. Another example on how chlorine interacts with the chemistry. We know that chlorine can react very quickly with ammonium nitrogen and form combined chlorine. And this is the research that was carried out in our lab by Dustin Meter. And what he did is that he evaluated the different fertilizers, and then he measured how much chlorine was left on the black bar after 2 minutes, on the blue bar after 1 hour. What he saw is that when there was ammonium in the fertilizer, and you can see these small bars, the concentration of chlorine went dramatically down, and that's the concentration of free chlorine. But if there's no ammonium in the solution, the concentration of chlorine remains relatively stable. We do not know what happened to urea. That's an unexpected result, but you can see that definitely there's also an interaction going on with urea. We also wanted to understand a little bit more on how that affected the efficacy of control. So what we did here is we had a solution with different fertilizers, ammonium sulfate and potassium nitrate. We mixed those with chlorine, and then we put the pathogen, and we wanted to see how efficacy was affected by this interaction. And what we learned from here is that what you see how many infected leaves were and the different concentrations of applied chlorine, that as long as there's chlorine, you see here, there is still control. If there's no chlorine, the incidence goes up. When there's chlorine, even in the presence of nitrogen salts, we still see some efficacy. So despite these results that seem very motivating, we still need to keep in mind, again, we are reducing the concentration of active ingredients. We need to, as a risk management strategy, ideally, we don't want to use ammonium fertilizers when we have chlorine. But if we have no other alternative because of different criteria, either economics or ease of use, and you're using chlorine, we also have an incentive that we know that something's being controlled under those conditions. An important criteria when deciding what the cost of chlorination of what the type of water treatment that you will use, it's the cost of treatment. And I'm giving here an example of chlorine because I don't have the time to go through all the efficacy and all the costs of the different technologies. But just as an example, we can see that if we have a hypothetical operation of 20 million gallons per year, and we dose at a rate of 2 parts per million, we can see that the capital investment by the different forms of chlorine, these are chlorine tablets, chlorine gas, or liquid chlorine, the capital investment varies, and therefore the capital cost per 1,000 gallons varies for each one. So when you're trying to make decisions, do you want to do a capital investment or do you want to pay more for consumables? And then you can see how consumables vary by each different types of chlorine. Labor was relatively the same, and then what's the total cost of treatment? Something that's really important when we're thinking about the cost of treatment and selection of treatments is that there is this trade-off between capital investment, these are the different technologies, and these are just representative dots on what is more expensive or cheaper. And you can see that there's this trade-off between capital investment and operation cost. If you have a low capital investment, you will usually get a high capital cost. And you can see this is the case for most of the technology. So when you're making the decisions, again, think about, do you want to make an upfront investment and lower operation costs, or do you rather be a little bit more conservative and not make a high capital investment and pay a little bit more afterwards? So the key points on sanitizers is, first of all, you have to match the sanitizer to the problem, so the known efficacy. Go back to the Water Education Alliance and make sure you see what your technology is and what problems are being controlled. If you don't have a technology yet, see what your problems are and match to the technologies that are known to be effective. Match them to other factors such as water chemistry. Like I provided you some examples of chlorine. The same thing, for example, we know that that other technologies, for example, like copper, they compete with some of the micronutrients in the solution. So a lot of things to keep in mind to match which technology are being used. And then in order to be more effective, also match your sanitizer to the size of the operation. That will reduce the cost of treatment, and it's very important that you reduce the cost of treatment, as Charlie has talked about cost. And then finally, when we're talking about cost, there is this trade-off between capital cost and operation cost. So make the decision up front and have very clear that there is this trade-off, and make a choice of how you wanna invest on your water treatment. So for questions or comments, I'm gonna answer the questions you typed today, but I will also be willing to answer any questions you want to email me. Right now, I'm still at the University of Florida, but next month I will be at the University of Connecticut. I still don't have my email for the University of Connecticut, but I'm very open to your questions and emails at any time. So, and with that, I would like to end.
Fantastic.
I would like to end the questions. Thank you.
Yeah, great job, Rosa, and it really did help to see the whole slide. So I'm not sure what the difficulties were there in terms of seeing it, but actually it worked out really great, and it's a good job on your part, because you adapted very well. So we do have 3 questions so far. Mind folks, if you have a question, just go ahead and type that into the question box. But let me get started on the ones that we do have. The first one was related to monitoring, Rosa, and it's where can we purchase petrofilms to monitor microbial load?
So the petrofilms are very handy and very easy to use. They are provided by 3M, which is the same company that makes the Scotch tape and other common supplies that we use at home. So it's 3M, and they cost about $1 per sample. You have to purchase 100 petrofilms in order to get. You cannot buy less than that, but they're really useful, and 3M is the right place to get them.
All right. The next question is, how beneficial is aeration to help with bacteria loading?
Aeration is really good when you're using ponds. The ponds are a very dynamic system, and I've heard that aeration helps on 2 ways. One, it alters the ecosystem of the bacteria, and therefore there's a shock and kills the bacteria and the different organisms in there. But it also creates a physical damage to the microbes in there. So aeration is very important because it affects the chemistry and also the physical aspects of ponds, and it's very useful to maintain a healthy pond.
Okay. Now the next question is there any particular water source, for example, well water, ponds, pond water, etc., that is more likely to develop biofilm?
Surface water in general and recirculated water are very rich in microbial loads. Well water can also develop biofilm depending on a little bit more in the chemistry. If there is iron in the water, if there is high concentrations of iron and there is a leakage of iron bacteria, can also be the case, but that's less likely to happen. The most common ones are surface water and recirculated water, just because they're richer in the concentration of bacteria that's present.
All right. Then there's another question. Can you expand on why 5-micron filters will not remove Phytophthora zoospores?
So that's a very important question, and I think it's very important to emphasize that, because we hear a lot on the industry about buying 5-micron filters. We hear that a lot and a lot. So there are 2 things that I would like to emphasize on the 5-micron filters and contrasting that to the zoospores. One of them is when we measure particle size in our lab, we learned that those filters that are reported to have 5-micron filters, you still get particles that are bigger than 5 microns on the other side after filtration. So, and we also took pictures of some of those filters, especially the paper filters, and the reported micron size is not exactly the pore size that we actually measured. So that's on one hand. And on the other hand, I think a nice analogy that we heard once from a professor is, if you think about how a mouse can go through the door of under the door, even though the mouth is a lot bigger than the hole on the door. You can also use that analogy to think about how zoospores can move through, because there's a lot of plasticity of zoospores that makes them move through the membrane. So keeping those things in mind, we need to understand that we can't remove pathogens with those filters. No matter what people tell you, take my word that you can't remove pathogens with those filters. The only alternatives are either membrane filtration or slow sand filtration. Not just any immediate filtration, but slow sand filtration can do the job as well. But that's very unlikely to be used in recirculated water just because of the flow rate. So that's a very important concept that I hope people take from this presentation today.
Okay, we're getting several comments as to how great this information is, Rosa, and one of the comments followed up their nice job with a comment that many of your points seem like they would lend themselves to a spreadsheeted matrix approach to decision making. Is this available now, or would you consider making it available at some point in the future?
I'm actually working on something similar to that, so that will definitely come soon. Because we work already on summarizing a lot of the things, and we're trying to wrap that up. So it's on the way. Stay tuned. Yeah. Follow me.
Yeah, that would be a kind of a nice segue for a follow-up webinar, maybe. So that's very good. Another question is, besides affecting the rate of water flow, what other deleterious effects can biofilm have for a grower?
One that's very interesting is that biofilm on the pipes can uptake a lot of the nutrients that are put into the nutrient solution. And it's very interesting. We were in Virginia a few months ago and talking with one of the researchers there. He was saying how they put a certain concentration of fertilizer on one hand, and then when they measure at the emitter, most of the fertilizers were gone. And that's just because there's a lot of biofilm in the pipe. So one is the physical, but there's also the chemical. And then so it will uptake the nutrients. And on the other hand, it's a place where pathogens can be hosted. So it affects the three parameters that we're taking care of. It affects the physical, it affects the chemical, and it affects the biological. So biofilm is very important, and it's very costly. I would say it's the most important problem for water quality.
Okay, and we've got another question is, if you're using UV for sanitation, and you don't filter to 5 microns, won't the particles remaining block UV effectiveness?
Yeah, that's an exception where you want to go as fine filtration as possible. You can, because UV, in order to be effective, has to have clear water. The turbidity has to be under NTUs. So it's very important that for UV specifically, you do need to go to a filtration that's really low, and 5 microns would be highly recommendable for a UV system. But I would say that's the exception. The other ones don't need to go to filter that low.
All right, and I think that's all the questions. Well, one more. Does chlorine dioxide interact with nitrogen fertilizers in the same way as chlorine?
That's a very good question. Chlorine dioxide has some benefits over chlorine, and one of them is that it's not as sensitive to the presence of salt. So the concentration of ammonia would not drop the concentration of chlorine dioxide as we saw it on chlorine. And the other thing that's very important is that chlorine dioxide is also less sensitive to pH. It is more effective at higher pH, but still it's less sensitive than chlorine. So it's very important also to distinguish that chlorine and chlorine dioxide, they're very two different technologies, so it's not affected by the presence of ammonia in the water.
Fantastic. Rosa, this has been a great job. Well
Thank
done.
You.
Well done. And folks, as I mentioned earlier, this webinar is being recorded, and the location of those recordings is at the top of this slide that I showed here, ellisonchair.tamu.edu, and you can do /multimedia/webinars, or simply click over here on the right-hand side on multimedia and go down to webinars, and that's where you'll see this archived webinar starting tomorrow, and of course you'll be getting an email saying when that's available exactly. So Rosa, thank you again. It's an outstanding job, and it's great information. There have been several comments in the question box saying, fantastic, this was great, and we'll probably have more follow-up questions for you. So you might expect an email.
Thank you for having me.
Yep, you betcha. And folks, thanks again for being here, and we couldn't do it without you. And again, you're going to be directed to a very short, very, 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 very short evaluation survey, but it's very important. So if you would just take a minute to complete that, that would be outstanding. And we'll look forward to seeing you next time, which of course will be this Friday. Yours truly be conducting an economic outlook webinar this Friday on 2014 and what it holds. So hopefully I'll see some of you then. Have a great week, and thanks again for attending.
Thank you. Bye-bye.
Bye-bye.